Okay, so we're continuing on with the 3.11 notes. And so we are looking at example 6. A ladder that is 10 feet long is leaning against the side of a building, and the base of the ladder is pulled away from the building at a rate of 3 feet per second. This is actually a very traditional, common related rates problem. I'll just tell you right now, because there's no need for this to be mysterious. This is something that's very common to show up on tests and quizzes. So you will see this problem again on homework, etc., with different numbers. It's likely that you'll see this on a test or a quiz as well. Maybe even both. We have some ladder, and the ladder is slanted. And it's 10 feet long, and it's leaning against the side of the building. That's how I know it's slanted. Here's my building right over here. Awesome diagrams, right? Fantastic. Okay, so here's my building, and it's leaning against the building. The base of the ladder is being pulled away. So my ladder is being pulled away from the building. And so I actually want to give some names to these sides. And since it's a right triangle, a very common way to name these would be A, B, and C, kind of using the idea that we might be using the Pythagorean theorem since this is a right triangle. Now, when it says the base of the ladder is being pulled away, this is a moving action, and notice it has a rate. So this right here, this 3 feet per second, is dA over dt. As we are moving this ladder away from the building, the base of it, the bottom of it, that's at the rate of 3 feet per second. So that distance at the bottom is going to be changing at a rate of 3 feet per second. And what we would like to know on this one is how fast is the top of the ladder moving down the wall when the base is 6 feet from the wall. So although this down here on the bottom is moving, we're going to be looking at what's happening at the instant when A is 6. We're specifically looking at the instant when A is 6. But I do want you to keep in mind that A is moving. So A is not always 6, but we're going to be looking at the instant when A is 6. So we know that A is going to be 6 is the instant we're looking at, and the rate of change of A is 3 feet per second. So, and what we'd like to find is how fast is the top of the ladder moving down the wall, because as we slide this base out right here, as we slide the base of the ladder out away from the ladder is going to start falling down. And so this is going to be moving down right here. And so what we're trying to find is the rate of change of B, and B should be moving downwards. And that'll also be in feet per second. So since we're talking about the side lengths of a right triangle, we can model this with the Pythagorean theorem. And that's going to be a common thing that you'll use if you have a right triangle and you're talking about the lengths of the sides, or the rate of change of the lengths of the sides. And so in this particular instance, however, one of these variables is not ever changing. A is going to be moving. B is also going to be moving, but C is unchanging. C is a constant. C is 10, because that ladder is not changing its length. And so because that ladder is unchanging, I can actually substitute in 10 for the variable before I do any calculus. Remember, our goal is to start with an equation, do calculus, and then substitute in for any variables that are changing. However, since C is an unchanging constant, I can go ahead and substitute that in right away, which is going to make my equation a little bit easier when I take the derivative. I'm now going to take the derivative of both sides with respect to t. And I can kind of tell that that's happening if I look at the units for the rate of change of A. And because 10 is a constant, its derivative is 0, and that's why putting in that 10 right away is super useful. Now, if you'd like, you could also divide everything by 2. It's not required, but it might be something that you find helpful if you'd like to divide everything by 2. And now I'm going to substitute in. I know that A is 6, and I know the rate of change of A is 3. What is B? Well, we have this right triangle, and we know 2 out of 3 sides of a right triangle. So you could either use the Pythagorean theorem or recognize that this is a 3, 4, 5 triple that has been enlarged by a scale factor of 2. So B is 8. And what I'm trying to find is dB over dt. And now I just have a simple algebra problem. I'll move that 18 over to the other side, and then I'll divide by the 8 and reduce. And so dB over dt, I'm running out of room here, ends up being negative 18 over 8, which reduces down to negative 9 over 4. And then you must have units. This would be in feet per second because the length b is measured in feet, and the time that we're comparing this to is in seconds. These related rate problems, if seconds is our unit of time measurement, we'll always have seconds on the denominator. What will change is the numerator on the measurement. So we're still dealing with this ladder. Okay, we're still dealing with this ladder that is 10 feet long as an unchanging value. And we are still saying that the rate of change, we call these A, B, and C, the rate of change of A is still 3 feet per second, regardless of what time it's coming out at that same rate all the way through. But now what we're looking at is the rate of change of the area of the triangle. So now, instead of talking about how the rates of a side length change, in which the Pythagorean theorem was useful, now we're talking about the area of a triangle. So I would need to use the formula for the area of a triangle, which is area equals 1/2 base times height. This is the formula I'm going to use. However, I might modify this just a little bit because the base and the height, I've been using A and B. So you could either relabel your diagram with calling those heights B and H, or you could use A and B, which is what I'm going to do. It's totally up to you. Now, again, we are going to be doing this at the instant where A is 6, which we already found out that that means that B is 8. By the way, we also know the rate of change of B now because we found it in part A as negative 9/4 feet per second. So those might also be useful things for us to use. Okay, so I'm going to take a look. Now, all of these are changing variables. The area is going to change as A and B change. So I'm not going to substitute any values until after I do the calculus. And I'm going to now do the calculus. And right here, I'm going to have to use the power rule, so be careful to notice that. So dA over dt would equal to, I'm going to think of this as the first and this is the second. So I'll do the first times the derivative of the second plus the second times the derivative of the first. Notice that this is with respect to t. We are doing all of these implicitly. dA over dt is what I am solving for. So that's my unknown quantity. And then A, we had said was 6. dB over dt we found in part A. Because this was at the same instance when A is 6, I can use that. We are still looking at that same moment in time. So that's negative 9/4. B is 8, and dA over dt was given to me at the very beginning as 3. And so when I simplify this, this is actually going to be my final answer, and I'm just going to have to think a little bit about units, but let me just multiply this together. Let's see, this would be negative 54 over 8, and I'm just going to reduce this really quickly by a factor of 2 and make this negative 27 over 4 for the first part. And then this would be 24 over 2, which is the same as 12, but I'd like it to have that common denominator. So I'll think of this as 48 over 4. And so when I subtract those, I'll get negative 21 over 4, and I've got to think about the units. Well, in a related rates problem, that unit is always just going to be the time unit. That's not going to change. We're not doing like a acceleration problem here, okay? This is not particle motion where acceleration would be time squared. That's not what's happening here. This is always going to be per second. But on the numerator, since it's talking about area, we know that area is always measured in units squared. So the area would be feet squared per second for the rate of change. Number 3, or part C actually. We are still looking at this ladder problem. The ladder is still going to be 10 feet. And we are still knowing that the rate of change of A is 3 feet per second. We are still looking at the moment when A is 6, which means B is 8 and C is 10. We can use previous information, so if we need it, we know that the rate of change of B is negative 9/4 feet per second. So because all of these were all at the moment of 6 feet for A, we can use all of that previous information. We even know the rate of change of the area if that comes into play, which it doesn't, but you maybe don't know that at the beginning of the problem. All right, this one. Find the rate of change at which the angle between the ladder and the side of the building, this angle, is changing when the base of the ladder is 6 feet away from the building. So you can choose what you call the angle. It's very common for people to call angles a Greek letter. So I'll use theta. You could certainly have chosen a different variable or a different Greek letter, up to you. And so what I'm trying to find is the rate of change of theta. And I have all of this helpful information over here to do this. But I need some type of equation that would allow me to have theta in it so that I could then take a derivative that would have d theta over dt as the result. So I must have an equation that has an angle in it. Well, my options are either sine, there's a formula for sine, remember sine is opposite over hypotenuse, or I could do cosine, which is adjacent over hypotenuse, or tangent. I could even, if I really wanted to get really complicated, use like, you know, some of the reciprocal functions of these. I'm not really sure why you'd want to do that to yourself, but you could. But these are all really useful, and you could pick one that you like. I will tell you that if you pick one that uses this side C, because C is a constant, it'll probably make your problem easier. We saw that earlier, that if you have a constant, that might be easier to solve. So both sine and cosine have that hypotenuse as part of the formula. So I would, oops, I wrote tangent wrong, huh? Tangent is opposite over adjacent. The one I wouldn't pick is tangent because it would involve both B and A, and both of those are variables, and I'd have to use quotient rule when I take a derivative. I'm not really excited about that idea, so I probably would not do that. I'll use sine. It's common for me to use sine, but you certainly could use cosine in this problem. I think on Earl's website that he does this problem 3 times with each of the 3 trig functions, if I'm remembering correctly. So if you're curious, you could take a look at his work. Okay. So I'm going to use the sine of theta as my equation, and that's supposed to equal the opposite side of theta, which is A, over the hypotenuse, which is C. But remember, because the hypotenuse is a constant value, I can replace that with 10 because the ladder is unchanging. A, however, must remain a variable because of the fact that A is changing, A is moving, all right, as the base of this ladder moves. Now I'm going to take the derivative. So the derivative of sine we know is cosine, but this is with respect to theta, or with respect to time. The derivative of A over 10 might be easier if you think of this expression as 1/10 times A. So then this is 1/10 times dA over dt. You don't use quotient rule here because 10 is a constant. This is a multiplier of 1/10. So it's just that coefficient times dA over dt. Well, we know what cosine is. Remember, cosine is adjacent over hypotenuse. So in this problem, the adjacent side length is 8. The hypotenuse is 10. You could reduce that to 4/5. d theta over dt is what I'm actually solving for. And then I know what dA over dt is because they gave that to me way back in the original stem of the problem. So if I would like to then find d theta over dt, I could just multiply both sides by 10/8. That's why I didn't end up reducing, because I've done this problem enough times that I knew that that 10 would reduce out. However, you know, you could do that computation in a variety of ways. Now the question is, what the heck are the units? We know in related rates that the denominator for the units will always be time. But what is the numerator? Well, we're finding the rate of change of an angle. And all angles in calculus are measured in radians. That is unchanging the entire year. Every test, every quiz, including the AP exam, your calculator should always remain in radians if you're using it. And anytime you're doing units with an angle, the units will be radians. And that is the end of our notes from 3.11.